So the final thing we're going to talk about today is visualizing Java streams in action. And the idea here is to give you a better gestalt, right brain oriented way of looking at what streams are doing to augment the left brain control constructs and flow of control and syntax and so on of the code. And we're also going to talk about how streams actually work in practice, which is not necessarily the way they appear visually when you look at them the first time. So we'll start by sort of talking about this in a high level, and then we'll show really what's going on under the hood. So streams enhance flexibility by forming this processing pipeline that composes multiple aggregate operations together. You can see here we pipe things together, as you saw, so that the output of one stream aggregate operation becomes the input to the next one. Each of the aggregate operations can filter or transform the stream, like our water filter, point of use filters we talked about before. And let's take a look at an example. This is a visualization of what we've been showing in code up to this point. On the right-hand side is the code. On the left-hand side is the visualization of what's happening. And if you want to play around with this, you can go to my EX12 folder in the Java 8 directory and take a look at the live lessons repository. So we start out by giving an array of names. So here's the array of names. These are all the character names in Hamlet. And then we use the of factory method to convert that array of names into a stream of names. So now we've got a stream of names. So the left-hand side shows visually what this looks like. And of course, we'd have dot, 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 because there could be more than just these three. We then go ahead and apply filter, and filter is going to get rid of all the elements that do not have either lowercase or uppercase h as their first character. And you can see what happens. Notice how poor Laertes and Claudius and Polonius and Gertrude and Ophelia and so on, they all got left behind. We only have Horatio and Hamlet left. And now we're going to take those two elements and we're going to use the map intermediate operation to capitalize them consistently. So now we're going to have a stream of capitalized names that are consistently capitalized. So we have Horatio and Hamlet. And then that's going to get fed into the sorted intermediate operation. And as you might expect, what sorted is going to do is it's going to collect all the elements together, put them into some kind of data structure. I think it actually sticks it into like a tree map or something. It puts it into a sorted collection. And then what comes out of that is a stream of sorted strings. So Hamlet comes first, followed by Horatio. So if you look at this, you can just kind of get this nice visualization of what's actually happening. And at least for me, you may feel differently because everybody learns in different ways. I always like being able to see what's going on. Now, we'll come back later and we'll use this kind of a diagram to illustrate other cool aspects, such as short-circuiting operations, run-to-completion operations. We'll also show how it can be used for parallel processing. There'll be some really neat things where you'll see how in a parallel stream, each of these different elements will be processed potentially by different threads in the common fork join pool, and we'll visualize that as well when we get to that point of the lecture. But before we do that, I want you to have a good understanding of how Java Streams processing actually works in practice. And this is important because if you don't have the right mental model, you'll come away thinking it works inefficiently when in fact it works very efficiently. So the way to look at this is the actual processing of a stream differs from kind of what it looks like when you visualize it. If you just look at it like this, it appears that each row of data is processed from left to right, top to bottom. So that's kind of what it looks like. That's kind of how I described it. But that is actually not how it works under the hood, and I'll explain why in a second. What happens in practice is each element is actually processed or pulled from the source from top to bottom, left to right for a sequential stream, or all in parallel for a parallel stream. Let's focus on sequential streams here just for the moment to avoid getting ahead of ourselves. So what's actually happening is when the terminal operation is reached, and I don't really show that here, but when the terminal operation, like for each, for example, is reached, then the stream will start pulling the data from the source, and we'll get Horatio. That'll turn into a stream. We'll then go ahead and filter it. We'll uppercase it, and then we'll do some sorting after we've collected everything together. So everything works from top to bottom, left to right. Now, why does it do this, you might ask? Two main reasons. Reason number one, doing it this way is much more efficient because we're keeping everything in one thread of control. We get what's called locality of reference. And this is also sometimes referred to as integrated layer processing in the networking research community. This is particularly important when we have parallel streams. So with parallel streams, each thread in the common fork join pool that's part of the processing pool will be working on an element and run it through all the operations in the common thread, rather than having what would otherwise be the case. Everything here would run in one thread, and then would pass it down to the next level, and that would run in a different thread, and then it passes it down to another level. That approach, which is basically sort of layer-oriented parallelism, is incredibly inefficient because of things like locality of reference and synchronization overhead and context switching and data movement and so on and so forth. The second reason is doing it this way supports so-called short-circuit operations, which are really nice because at some point, if you have some operation that needs to short circuit, like limit or take while or drop while and so on, then as soon as something is hit that requires things to stop, everything comes to a screeching halt, and you don't do any unnecessary processing. And if you do it the way that I just showed you here, that's what you get as a result. If you were to do things like this, then there'd be a lot of extra processing, even when the data was going to get thrown away once it reached one of those short circuit operations. We'll talk more about short circuit operations later, so don't worry about that too much right now. So that's the end of visualizing Java streams. You'll see a lot of visualizations in other lectures later.